Okay, Honors Chem. Today we are going to take some of the things that we learned last time in terms of reaction rate and things that affect reaction rate, and we're going to apply mathematical principles to actually figure out what the reaction rate is today. So before we dive into figuring out mathematically how we determine the reaction rate, let's do a little bit of an algebra lesson with exponents. Okay? So I have this proportionality symbol in here, which you probably have not seen before. It just means that A is proportional to B in some way. It doesn't mean that A is equal to B, it's just proportional. We don't have an equal sign there because we don't have a constant. And we are also going to eventually learn how to determine the constant in these rate laws. Okay? So let's do a little experiment. If I have 1 to the 0 power, what would that be? That would be 1, right? So let's double that. If I have 2 to the 0 power, that is also 1. So if I double the amount of B, it makes the amount of A constant. It doesn't change. There's no change here. Okay? What if I triple B? 3 to the 0 power is still 1. So tripling the amount of B still makes the amount of A constant. There is no change. Okay, so if I was to graph this on a Cartesian graph where B is on the X and A is on the Y, I would get a graph like this. I would get a constant line. It didn't matter what B would be, A would always be the same. Okay? All right, let's go if B is to the first power. So if I have 1 to the first power, I get 1. Let's double it. So 2 to the first power, I get 2. So doubling the amount of B will double A. What if I triple? 3 to the first power is 3. So tripling the amount of B will triple, or 3 times the amount of A. So if I do a relationship on a Cartesian graph, I will get a linear graph, right? This is a nice straight linear graph. All right, let's do B squared now. So if I have 1 squared, A would be 1. What if I double it? 2 squared, A would be 4. So doubling the amount of B would quadruple A, right? Square. What if I triple it? 3 squared is equal to 9. So tripling the amount of A, I would get, or tripling the amount of B, I would get 9 times A. And there goes my computer, not wanting to think. Okay, 9 times. Okay, so if I did a Cartesian graph here, I would get an exponential equation. Okay, so we're going to figure out how to use these types of relationships to determine rate law. And we're also going to get rid of this proportionality symbol with an equal sign by determining a rate constant, K. Okay, so for every reaction in the relationship between the rate of the reaction and the concentration of the reactants is called a rate law. Okay, so if I have A plus B making D, my general rate law, and sometimes it's called the initial rate law, okay, sometimes it's called the initial rate law, the rate, and sometimes this is symbolized with a capital R, is equal to K, which is our rate constant for that reaction at that temperature. They are temperature specific, multiplied by the concentration of A. Remember, these square brackets mean concentration, molar, or moles per liter. The concentration of A raised to some power of M and the concentration of B raised to some power of N. Now, M goes with A, and N goes with B. And M and N can only be determined by experimental data. So we have to look and run that experiment and look at that data to determine what those exponents are. Okay? So here we go. M is the order of the reaction with respect to A, okay? And N is the order with respect to B. So the overall order is the sum of M and N. So if I want the overall order, I just take the exponents and I just add them up. So let's look at some data and let's learn how to create these rate laws, okay? So we're going to consider this following data. Now, when we determine rate laws, there are a couple things that you need to be aware of. We are going to compare trials against other trials. So here I've got trials 1, 2, and 3 in this example 2. Now, when we compare trials, we need one of the reactants to be held at a constant concentration. So we look for two trials where one of the reactants is held at a constant concentration. Okay? So, for example, if I look at trials 1 and 2, trials number 1 and 2, my concentration of B, my concentration of B, trials 1 and 2, is constant. So that means I can look at A. I'm going to look at A. Okay? So I can look at A as long as B is held constant. So when I look at A, my concentration between trial 1 and trial 2 doubles. 0.2 is double 0.1. So I'm going to look at the rate now. What happens to my rate between trial 1 and trial 2? 2 times 10 to the 3 compared to 4 times 10 to the 3, my rate also doubles. So then I have to look and see, is this an x to the 0 where it's constant? No. Is this an x to the first where it goes up the same way? It's linear? Yes. This is a linear relationship. So that I know the rate with respect to A is first order. So when I write the rate law, my exponent for A is going to be 1. Okay? Let's look at B now. So to look at B, we are going to need to look for two trials where A is constant. So our example here, we need to look for two trials where the concentration of A is held constant. And those are trials number 2 and 3. Notice A is being held constant here, but B is changing. So I can look at B. Now, the reason I do that, the reason I want the other reactant held constant is I want to know that the change in that reaction rate is solely due to the change in the concentration of that one reactant that I'm looking at. If the concentration of both reactants are changing, I don't know what that change is doing compared to either reactant. I need to make sure that at least one reactant is held constant so I can look at the other reactant. Okay, so I'm going to look at B here. So if I look at B, B is doubling. It's going from 0.1 to 0.2. Let's look at our rate here. Our rate is going from 4 times 10 to the negative 3 to 16, which means our rate is quadrupling. So is this an x to the 0 where it's constant? No. Is it x to the 1 where it's linear? No. This is x squared. This is a square, right? 4 is a square of 2. So our order with respect to B is second order. That means that our concentration of B when we write the rate law is going to have an exponent of a square or 2. Okay? So let's look at these questions. Question A, what is the order of this reaction with respect to A? We saw that it was linear, so our order with respect to A is 1. What order is the reaction with respect to B? We saw that it was a square, so it is going to be a 2. What is the overall? Remember, the overall is the sum of the exponents. So if I have 2 plus 1, I'm going to have an overall order of 3. I just add up all the exponents. Okay, so if I write this rate law, remember, we're just going to go off of the general rate law, where we have our rate is equal to a constant, and we don't know what that constant is yet, but we do know the exponents for A is 1, and we do know that the exponent for B is 2. Now, you can look at that exponent 1 on that A, and an exponent of 1 is always implied, so you don't necessarily have to write it. So I would be totally correct by writing that my rate is equal to K multiplied by my concentration of A multiplied by my concentration of B squared. Both of those would be acceptable. Okay? So then the next thing we have to do is we have to calculate our numerical value for the rate law K. So let's take this rate law that we just wrote and we're going to isolate K. So if I isolate for K, K is going to be equal to our rate divided by our concentration of A divided by our concentration of B squared. Okay? Now, honestly, I can take any one of these trials and plug in my rate, which is this, my concentration for A and my concentration of B, and calculate the rate constant. Now, I'm pretty lazy. I usually just grab the first trial because that's usually the easiest one to grab. So that's what I'm going to do here. I'm just going to grab the first trial. So let's plug in our things. So our rate is 2.0, and our units are mole per liter second. Okay? And then the next thing is we have to divide by A. So if I divide by A, my concentration of A is 0.1 mole per liter. Remember, because this is molar. And then my concentration of B is 0.1. Let's see. I'm going to just put in the mole per liter, and we've got to square this one. Okay? So I'm going to take 2 times 10. Oh, that should be times 10 to the negative 3. So when I do the math on that, I get 2. Now I have 3 sig figs on each of my numbers. So this is going to actually be 2.00. Now let's figure out what's happening with our units. Okay, so we've got a whole bunch of moles, we've got a whole bunch of liters, and we've even got seconds in here. So let's figure this out. And it looks like my computer is thinking. Okay, so my liters here will cancel, and my moles here will cancel. So I'm really left with liters squared and mole squared, liters squared on the top, mole squared on the bottom, and seconds on the bottom. So I would have 2.00 per second per mole squared on my units when my computer lets me actually write. I'm sorry that my computer is having such problems. Thanks for being patient, guys. We'll give it another minute or so. Okay, so my liters here cancel, my moles here cancel. Oh, and here it goes again. My moles here cancel, and I'm left with second and the liters squared and moles squared. So I could also write this as 2.00 second molar squared, big capital M molar squared for my rate. Or sorry, not for my rate, for my constant. Okay, so I can now use that constant in any problem that this is going at, that this reaction is going at this temperature. Okay, so now let's figure this out. What happens if the concentration of A is 0.25 molar and the concentration of B is 0.33 molar? What would be the rate? So I can use this equation that we generated and just plug in things. I now have my rate that I was generating. So my rate is 2.00, or not my rate, my constant. We want to know our rate. So my rate is going to be equal to 2.00 per second. And I'm going to break out, I'm going to have molar squared. And I need to multiply by my concentration of A, which is 0.25 molar. And I need to multiply by my concentration of B, which is 0.33 molar squared. Notice I'm just structuring it off of that equation that we had up here. Okay, so when I do that, I get, let's see, I get 0.54. I only have 2 sig figs on these. So I will get 5.4 times 10 to the negative 3 for my rate. Let's look at my units. My molar squared cancel here. So I'm going to get molar, or moles per liter per second. And that's what I should get for a rate. I should get molarity, moles per liter per some unit of time. So there we go. All right, let's do another example. We're going to consider the following data for a reaction between hydrogen and nitrogen oxide. So we have hydrogen and nitrogen monoxide going together to make water and nitrogen gas. Okay, now we have got to look for some reactions where the nitrogen monoxide is held constant so that we can look at hydrogen. Okay, so what reactions are nitrogen monoxide held constant? Reactions 1, 2, and 3. So we're going to look at trials 1, 2, and 3 to determine the rate order with respect to hydrogen. Okay, so between trial 1 and 2, my concentration of hydrogen is doubled. What happens to my rate? It is also doubled. Okay, between reaction 1 and 3, my concentration is tripled and my rate is also tripled. So my question is that constant? Is it linear? or is it squared? If you said it is linear, you are right. Okay, so that means our order is 1. So our order with respect to hydrogen is 1. Okay, so our exponent for our hydrogen concentration in our reaction equation, our rate law equation, is going to be 1. Okay, now we need to determine the order with respect to nitrogen monoxide. So we need to look at reactions where hydrogen is held constant. So if I do that, I need to look at trials 4, 5, and 6 because my hydrogen is constant. Okay, so let's see. If I look at 4, 5, and 6, and I look at nitrogen, this is doubled. Okay, what happens there? Let's see, 12 divided by 3 is 4 times. Okay, let's look at between reaction 4 and 6. This is 3 times. If I look at this, let's see, 27 divided by 3 is 9 times. Okay, so is this constant? No. Is it linear? Does it go up in the same proportions? No. Does it go up in proportions like a square? Yes. So this is to the second order. Okay. So our reaction order with respect to nitrogen monoxide is a square. So second order. Okay. So now we can create our equation. So our rate is equal to some constant multiplied by my concentration of hydrogen to the first power multiplied by my nitrogen monoxide concentration to the second power. Okay, so that is going to be my rate law. Now we need to determine K. So if I want to determine K, let's isolate K. So K is going to be our rate divided by our concentration of hydrogen, also divided by our concentration of nitrogen monoxide squared. Okay, so I'm going to grab the values from the very first line because, that's the easiest one to grab. Okay, so our rate is 20 molars per minute. Hydrogen is 1 molar and nitrogen monoxide is 6 molar. Okay? All right, so here we go. We've got 20, oops, I don't want that pen. I want this one. So our rate is 20 molar per minute. Okay? And then my rate for hydrogen is 1 molar, 1.00 if I want to get my sig figs here. And my rate for, or my concentration for nitrogen monoxide is 6.00 molar. Let's write that better. Okay, now I'm going to pretend like this is 20 with a decimal place behind it so that we can get 2 sig figs here. Okay, so if I take this, I'm going to take 20 divided by 1 divided by 6 squared, right? Because we've got to square this one. And I will get 0.5 repeating. So with 2 sig figs, I'm going to get 0.56. And let's look at our molar. So let's see, that molar cancels out. So this will be per minute molar squared for our unit. Okay. Calculate the rate of our reaction in experiment 7. So if I look at experiment 7, I'm going to grab this data. So I have 0.245 for my hydrogen concentration. I have 3.78 for my nitrogen monoxide concentration. I don't have my rate, so that's what I need to figure out. So I'm going to use this equation that we did before, and I'm just going to plug things in. I want to find my rate. So my rate is equal to my constant, and I'm going to have 0.56 per minute molar squared times my hydrogen concentration. My hydrogen concentration is 3.78 molar multiplied by my nitrogen monoxide concentration, which is 2.45 molar squared. Now I want to make sure that I've got those numbers correct. So I'm going to just scroll up 3.78 and 2. Yeah, that is correct. Okay, so when I do that, and I'm not going to use this rounded number, I'm just going to use what I've got in my calculator, which is the 0.5 repeating. That will give me to 2 sig figs. That gives me 12.6. So to 2 sig figs, that will give me 13. And it looks like my computer is thinking again. So that will give me 13. And my units, let's see, my molar squared cancels. So this will give me molar per minute, moles per liter per minute. Wow. I'm sorry that my computer likes to be so slow. So you'll get 13 moles per liter per minute on that rate law. Once I can write it, this will be great. I'm so sorry. I thought I had taken this, I just updated my computer and it's still totally glitchy.